Guys, welcome back to my YouTube channel. I hope you're doing well. Today we'll be looking at this is a Shrinkage allowance. It's N6 strength of material. This is the introduction, by the way. So given 1.3.5 Shrinkage allowance says to obtain the requirement initial pressure at a common diameter of a compound cylinder, the inside diameter of the outer cylinder must be smaller than the outer diameter of the inner cylinder. Okay, the shrinkage allowance is calculated at the common diameter of the compound cylinder, at the shrinkage allowance at the common diameter. Take note, not anywhere, at the common diameter. This is achieved by calculating the change in diameter. First is achieved by calculating the change in diameter of the inner and the outer cylinder at the common diameter individually, then adding the two values together. Okay, what do they mean? Let's see here. General formula for change in diameter for what? For a sleeve. You see, general change here is talking about change in diameter for a sleeve. This is a strain, as you can see. It's equals to hoop stress. Actually, this you can write this. The strain is equal to 1 over E, like this, Young modulus of elasticity. Then hook stress minus Poisson ratio. Then this is a radial, like this. Yeah, like this. Call this, it's a strain. This is how you calculate the strain. This is a strain, right? Because why you're supposed to calculate the strain is because the change in diameter, guys, this is the change in diameter. The change in diameter, actually, you know that the strain is equal to the change of something. Remember, during N5, we know that strain is change in length over original length. Yes, must be change of something over its original. So same applies. This can also be change in what? In diameter. That symbol like that, this symbol represents change in diameter over dx, which is the one that we are looking at, the original diameter. So you see what is going on. To calculate this change will require to have the strain, but the strain is calculated using this formula, right? The change in diameter, right? Then the change in diameter here, as you can see here, the change in diameter is equal to what? If you substitute this here, there, as you can see, if you take this whole, you plug it there, this is the formula that you will get there. That is the formula that you will achieve. So we will achieve this formula. That is the formula. But however, you must take a note. The change is equals to that. The change in diameter is equals to this formula. The strain is given by that. That is how we calculate the strain. So far the change in diameter, nevertheless, here is the change in diameter. Will be equal to the of the sleeve is dx there over E hook stress minus Poisson ratio, the radial. That is what we have there. We've said this is the strain energy, hook stress, radial, Poisson ratio, E Young modulus of elasticity, change in diameter, the change where they must be calculated, the diameter there. Hopefully you know this, Pascal. So the formula for, you've seen the formula for changing diameter of the inner cylinder at where? At contact diameter. This was for the sleeve. The change for a sleeve. Here, this is a formula for inner cylinder at contact, at the contact diameter. So the change in that I want to take something from these two, we have the change. Here we'll have what for this, for the sleeve. This will be the change for the sleeve. You see the correspondence. So I want you to check something. You want the change in the inner. Also here must have a common, must take place at the common. The inner takes place where at the common. Check here the common diameter. Then inner, hook stress at the inner, but the radial at what? At the common. At the common. Yeah, we'll see this during calculation, these formulas, guys. You shall see this. As you can see, in a common, inner, then see these tools. The radial is common, inner. We shall see. Shall see where this is a change in the inner diameter, change in the inner diameter of the cylinder, common diameter, modulus of the inner, hoop stress of the inner cylinder, Poisson ratio, common diameter. We shall see formula for now. Formula for changing diameter of the outer at contact. Remember, first was the inner, now it's out. Here we'll have outer, out, common. You see the differences here. We shall see how we go about calculating the change in diameter for now. Here, this is a shrinkage, the formula for shrinkage allowance for compound cylinder made of same material. Check there, take note, same material there. So that change in diameters, ensure that this sign is not the change, is the shrinkage. Check here, we represent change in diameter by this symbol, shrinkage by the delta. You see this triangle represent what? Shrinkage allowance. This one is a change. Do not make a mistake. We're used to change lead. Often we're using this symbol for what? For change, but this one will be for shrinkage, will be for change. Then this one will be for shrinkage allowance. So yeah, shrinkage allowance is measured in meter. So shrinkage allowance is common, Young modulus. Check the outer. There is no voice. Do not put voice ratio. There is no voice ratio. Outer hook stress, inner hook stress. We have hook stress is only here. Hopefully you check the hook stress is only. Okay, they shall see when you are doing. There are two main now. The formula for shrinkage allowance for a compound made of what? Different material. Now first was for same, now it's different. Now the change will be, the shrinkage allowance will be the change in the outer diameter minus the change in the inner diameter. Then we know how we calculate the change here, right? Hoop stress minus radial outer minus hook stress inner minus common, like this. We know this formula. This formula you'll be given, if I'm not mistaken, some of them. Let us check here what they say here. The outer cylinder will increase in diameter plus because of the hoop stress, the intensile. The inner cylinder will decrease in diameter because of the hoop stress is negative. The negative sign automatically adjusted in the formula. This means the switch. Okay, yeah, we'll see this when let us see if we can take an example. Let us take this example. Let's check. Let us check on this example. It's an interesting example, though. It's an interesting example, otherwise. So we've given here a sleeve with an outer diameter of this 150 and inside diameter of this is 200 milliliter long. Okay, that is the length. A shaft solid of this, a solid shaft of that 120 millimeter in diameter is to be pressed into the sleeve. So you see what is going on here is to be pressed into the sleeve. right? So these guys, yes, you can see guys here, we're starting with this is a sleeve with a solid shaft. We've discussed about this sleeve with a solid shaft. Hopefully you remember. This is a cylinder here will have what? A solid shaft. Remember I said here at the contact diameter, the hook stress is equals to, the radial stress is equal to hook stress at the common diameter should equals to what? Um, you can say the hook stress is equals to radial stress, whereby also is equals to pressure. Remember at the common diameter, if you're given the shaft, remember that. Do not forget that again. We've discussed about this. So this is what we're given there. A sleeve with the outer diameter and side diameter of that of 199.9 is that long. The shaft of 100 and this is to be pressed. The force that on this diameter. So how does it goes? Then says here calculate. Given young modulus, we're supposed to use this, but somehow okay, we're given young modulus there. Says calculate the force necessary to press the shaft into the sleeve if the coefficient of friction is that. We've discussed about the force, isn't it? The force is, if you still remember, the force is equals to coefficient of friction multiplied by the pressure multiplied by pi common diameter length. Remember the pressure is the same as we have to have radial there. The pressure is our radial. So the aim is to calculate if we can have our radial here, we can simply have that pressure is equals to radial. Okay, it's fine. So this is what we have. Let us sketch our internal pressure, internal pressure diagram. You can say now we can answer this question. What we need here is our sketch with remember this guys, from here going there we'll have our hook stress, our radial stress. What's wrong with me today? Goes like that. There is zero portion. Isn't it? Here we have zero. We have zero, then our hook stress will goes like that, but won't reach zero. Isn't it? Here we now have positive with minus. Isn't it? So this is for the hook, this is for the radial. Okay, this is the internal pressure graph. Remember here, this is not a compound, guys. We have a sleeve and a solid shaft. I've discussed about the solid shaft and the sleeve. We're using this, right? So what is the pressure here at this point? We're often given, I don't know if we're given it is in this scenario, on this scenario, what is the there at that point. We're often given that. We don't know that value, are not given there. Take note here, we are not given the radial stress there. We only have this point in this question. There is nothing talking about. If we read here, I see anything talking about the internal pressure or hook stress or radial stress. We are not given radial stress here. So let us give this radial stress here. Let us call it, we want this radial stress. How can we, let us name this. Now we're given unknown. We can call it pressure, or we can call it P, or we can say Y. Any letter of your choice, guys. can say it's radial, you can say it is P, you can say it is Y, it's X, or you can say it's up to you, X, or you can write it R, radial what, you can write, it's up to you either way, guys. So this all noise, this is a, remember we'll have a common diameter when I did in the shaft. This is common diameter, this is a outer diameter. If you have a sleeve and a solid shaft, this is common, this is a right ends. That is what we have. Right, our outer diameter is 150, the inside diameter is 1.1 no, it's 119.9. Here we have 119.9 millimeter. This one is 150 millimeter. So yeah, we don't know this value. I can call it what? Yes. Can call it, what can we say about this? Call it P or radial at this point. Okay, let me just, because it's equal to pressure, I can say P, because I don't know it, but I know this is radial. I can say P or Y or X, I don't know. So all we know now, we know that delimited, we know that radial, we know that due to fit to the sleeve, we know that can say at the internal diameter. We're working at the internal diameter now. We're telling the examiner which diameter, when common diameter, which is 119.9 millimeter. So there, the radial stress, we have given it to be what we call it, we have called it to be P, right, which is to be P megapascal. We don't know that, right? We are working at this diameter, at that diameter, working at this diameter so far. Then we don't know, is P megapascal, we can call it that, we don't know. Is P megapascal, is in either way, right? So that is what we have, isn't it? All right, so we don't know that. Okay, so since we don't know, but what about this? We don't know this. We know that radial is given by A minus B over D squared. Then this is equals to P. We don't know there. I can say P. Call it P. Why I want that? We're supposed to get it whether we like it or not. Remember, we're supposed to get it. Supposed to get it. The pressure is the one that is in the radial stress. The one when you're calculating the force, we're using the one that is radial stress. You're using the radial stress there. We'll need that value of the radial stress. Either way, when you're calculating the force, pressure, we'll need that pressure. Either way. So we are forced, because of the formula that we know, because we know that the force is equals to coefficient of friction multiplied by pressure pi dcl. We are forced to calculate it. We have to know it. So A we don't know, minus B over the diameter there, which is that diameter. We have the diameter will be 0.1199 squared. Remember now, divide that by 1000, isn't it? Convert this to be in meters, right? like take your calculator, you say 19.9, you divide all of that by 1000. That is what you're supposed to get, isn't it? Right? So you can call this, okay, this you can say there's nothing we can do. This can call this equation 1. Then what about what we know? We don't know not what we know again. Here at this diameter, the radial is 0. Then now to them at the outer diameter, or you can just write the diameter, this diameter, whereby the diameter there, whereby is 150 millimeter. So the radial stress there is equals to 0 megapascal, as you can see here, that is 0 megapascal. So what is this now? The radial, we know radial is simply equals to a minus b over d squared. Here this is 0, a we don't know, minus b, the diameter there is 150, will be 0.15. We square this, can make a the subject, have b to be positive like that, then I square, and I could call this equation 2. Then it's a matter again of the algebra. It's a matter of the algebra again. All right. The matter of the algebra again. Okay. The matter of the algebra. Now can say substitute equation 2 into 1. 2 into 1. Here it's our 1. Let me just, then I will paste it here. Right, here's our equation 1. Where I see this is a, right? Where I see a, I'll replace there. I'll replace a, I'll put all of that stuff there. So the p will be equals to, what is a there is b into 0.15 square, 0.15 squared minus b to 0.1199. Square this. This I've been discussing about this, guys. This is same as 1 over 0.15 squared b like this, minus 1.1199 squared like this. So just subtract this, subtract on a calculator, press this. I'll have punch that there. Let me check. 1 over 0.15 squared minus 0.199 1199. Square this. What is the value that I could get? Did I square the value there? Yes. Alright, remember I have to find b. Okay, this will be minus, this is interesting. Here examiner, they were trying to play fence. This will be negative 20 minus 25,11. Let me say 6b. But we're supposed to have a and b, isn't it? First we calculate a and b, so I'll make b the subject. Remember, we're supposed to have b as we always, so we'll divide by minus like that, divide by minus 25,116. This will fade away. You'll get b to be equals to what? Remember, the p divided by minus 25,116, this is the same as this one there. You simply just punch that. This is the same as like this, right? This is the same. You just punch 1 over minus 25,116. Then there's p there if you know your maths, right? Negative 39, right? As you can see, you'll strictly have accurately have negative 39 comma, on my calculator got 815, but here there is 2. Let me just round it to leave it to 3 decimal digit. Then I'll say times 10 to the power of minus 3. So you see, this is the value of b, but here we have p. Remember, this is like this, we still have the p there, still have p, then this will be what? P. Do not forget the p, we still have p. Do not forget your p there. Understand? Remember, still have p. We just applied the math there. Remember, we have divided p by minus 25,116. So we just took that. We still left with p. Do not forget that p. So this is b. That is how b it is. That's how p is. Because now this, you see there's p. This always will be again equation, call it 3, because you see this is an equation, is not the accurate value. Okay, that is b. Then obviously we have now to, we know if we have b, we always, if we have b, we always now have to find the value of a. As always, we are doing what we are knowing. Remember, a, we have to find a again, isn't it? Oh, I hopefully we did make a the subject here. Here we have a. Remember, you follow your method, what we know. After finding a, maybe we'll be confused by this, I don't know, but I can write it again 3. But remember, you used to find b, then you find the value of a, or you get a and find the value of b. So still apply what you are knowing there. Where you see p will replace with that, a will be equals, where we see p will be minus 39,815 times 10 to the power of minus 3 p. Do not forget your p, all over 0,15 squared. Alright, so punch on your calculator this like that, over that. Supposed to, if you punch that, you'll get that your a will be equals to, remember this is the same as, if you do not be confused by that, be same as again multiply by p. You can punch this like that on your calculator, then you multiply what you have by p. So I'll make the maths to be simple for you there. You'll have, let me, minus 39,815 times 10 to the power of minus 3 divide by 0.15, we square this, will be negative 1 comma 7, or will be 7. Why? Because we have 6 9. If you round off 5 like this, if you round off, this will affect the 1. So this would be comma 7 p. Remember, with p we multiply by p. Okay, and there will be p. You can call this equation 4. So we have the value of a and b. Now we know what we're supposed to do. We can find our radial stress there, isn't it? You can find your radial stress and your hook stress. It's up to you, but now the aim is to calculate the force. What is important for us is to find to get this radial. Just to get this radial. But we can, there's something lacking in this question. There's something lacking. We have given, you must check something. There's something lacking here. This question, the examiner, they made a mistake. Okay, we have E. If we have E, obviously, guys, here they're supposed to give us shrinkage. There's the extra. It's not you guys, it's them. They must give you the shrinkage allowance. It must be given. Shrinkage allowance must be given to us. Shrinkage allowance here is 0.1 millimeter. Calculate or write. Supposed to be given, or here, and the friction is that, and you're supposed to say the shrinkage allowance. If we're given shrinkage allowance, supposed to be given there. Must be there on our. It must be the shrinkage allowance must be there on our question here. It must be here. It must be given to us. So it's 0.1. The shrinkage supposed to be given, provided that we have a shrinkage allowance there. So this is what we have so far. All right, guys, we have the A and B now, isn't it? What done with A and B? Okay. Now there's something interesting. Since you have the shrinkage, we want the value of P, obvious. This is a high order question, but it's not that much difficult. Remember, since you're given the shrinkage allowance, they were supposed to give you the, can ask, if you are you can ask your teacher, this is wrong, I don't know, but it's supposed to be given the shrinkage allowance. And according to my understanding, yeah, actually I'm correct, supposed to be given a shrinkage allowance. Shrinkage allowance. We know the shrinkage allowance given by formula DC at the common diameter over what E. Then remember, this is must be hook stress. We must deal with the hook stress. Hook stress of the outer diameter, right? Outer part, outer, then minus the hook stress of the inner. Remember, I've talked about this. I've talked about that. Or let me show you the hook stress. The radius shrinkage is given by delta. It's supposed to be the common diameter over Young modulus. Then supposed to have the hook stress of the outer minus the hook stress of the inner. Do not forget that. It's like this, guys. So all right, this is the information you're supposed to have. All right, because you have to have the hooks. But the nice thing, all right, we have talking, this is a shaft. It's a sleeve and a solid shaft. Remember, I've discussed about this. I said here the contact diameter, the radial stress is equals to hook stress, whereby also all of this is equals to pressure. So right, we'll take advantage of that. All right, guys, since we know this, okay, let me just put this aside a little bit. Okay, we have A and B now. Okay, let's find the, we can find the radial, you can find the hook. It's a one and the same thing. It's up to you because they will be the same, isn't it? At that time, at the common diameter, at the common will be the same. So I can say now we know that P okay, we have the P the what we call this, the okay, we'll suppose, okay, let me just say the hook stress. I want to say the hook stress, we know the at our diameter 1, we know the hook stress is given by the formula, right? We have the value of A, but A is this, including B minus 1,777P plus, what is B? B is all of this, it's all of this, guys. I can copy it on my screen like this, then I plug it here like that, make it. So this is value of what of B, this is what we'll have, then this will be over, remember the diameter is this, the one that we're looking at would be 0,1199 then squared, right? So what is the hook stress here at this diameter? Okay, supposed to punch this. Remember, this is the same thing, guys. There is PP for you, for your calculator. Punch this and add the plus on your calculator also, then press this aside, add those. After you've add those, you will get that, you apply your math, this would be minus 4,539 what P, because of P. Okay, we have this now. So guys, remember this was this is for it is there at the common, it's for at the common, here at the common, unfortunately at the common diameter, at the common, when you're given a level, this is equal, these guys are equal, they will be equal at the common. If you are given a shaft and a sleeve, we've discussed about this, we have found the hook stress there. Since this they will be equal, we know that at the shaft, if you have a shaft, the common diameter, the radial stress is equals to hook stress, whereby is equals to what, pressure. So will be the same as that, we know that. So since we know this is the same, either way, that means all of these values will simply have hook stress, even the radial will be equals to 4,539P. Why? Hook stress and this, all of this will be equals to that. Why? Remember, this, the internal pressure is the same, internal pressure is the same as this, same as that, at that when you're given a shaft, and or not just a shaft, solid shaft. You're supposed to roll a solid shaft. You can say the solid shaft with what? The sleeve. I hopefully you'll understand this. I'll understood this when we have pressed. Okay, since you know that, but however, now we have our hook stress. The aim is to calculate P. How can we make P the subject? So we know that the shrinkage are given now, the shrinkage allowance. We know that, or I can write this in name so that you can see out shrinkage allowance. It's equal to common diameter over a modulus of elasticity over the hook stress of the outer minus the hook stress of the inner. All right, whereby equagically, we know that is dealt equagically. If you want this in this manner, equagically, yeah, must use to that delta. So far, shrinkage allowance I said is 0.1 millimeter. So this will be 0.1 times 10 to the power of minus 3. Remember, must be in meter, right? So is that it's equals to common diameter. The common diameter now. What will be the common diameter? Check it out. Common diameter now. We cannot use just round off this. Why? Because just check. Common. If you we will fit this on this region, on that common on this. Let's say we have that, then we are forced to put the shaft there. So that will increase, will be exactly 120. Remember, when we are calculating that, now we're focusing on the sleeve, but now because when you're calculating this shrinkage allowance, your common diameter, remember guys, here we have this. I want you to check something. Maybe you're supposed to understand me. Let me just do this. It's a sleeve. It's our cylinder here. Remember, when we're calculating A and B, we focus on the cylinder, not on the shaft. We're given this to be 150 millimeter. The outer one, the inner, we've given inside diameter to be 1,1,1. We've given this to be what? 1,9, right? 9,9 millimeter. But now we're fitting, we suppose here we've squeezed, we put now the shaft which is 120 millimeter here on this. Obvious, when we enlarge, this will be the same. If we force it, remember this is small, will increase a little bit to what? 220. We will consider that when you are under the shrinkage. But when you are calculating A and B, do not use a shaft. Does not fall under A and B. Use what you are given. But here, shrinkage, remember now, it's how things change, how it's written. Our common diameter will consider the one will be the one of the shaft. The one of the shaft will be the diameter of the shaft, whereby it's 120 of the shaft. Common diameter will be the one of the solid shaft, which is 120 millimeter, right? This is same as 0.12 over Young's modulus of elasticity we've given was 200 times 10 to the power of 9. Obviously, it's in gigapascal. Into now hook stress. We have the hook stress now at the outer, and the hook stress at what? At the inner. It's at the shaft or at the common. The shaft, no, hook stress does not act at the shaft, but I'm talking at the internal diameter. There we know between the shaft and that, we know that we've given, but the hook stress there at the outer hook stress at the outer. what is the hook stress at the outer now? The hook stress. We don't know the hook stress. Remember, this is the same. Oh guys, hook stress at the outer. We don't know this hook stress. We don't know the hook stress there, but we can call this. You can just say it's P. We don't know that thing there. 1P. So to be safe, we don't know that. So it is nice. So here we can say the out. We don't know. I can call it P because we want the P. We have that to be P minus. Now we had that to be, it was negative again. We'll have this to be minus again 4 point. We've calculated this to be minus 4 here, minus 4,539. P like that. All right, this is what we have, guys, so far. Right, this is what we have. This is what we have. So okay, we've taken this from here by also this we have the P by. Okay, now this is what we have. Now it's a method of maths. Okay, here we have 0,1 times 10 to the power of minus 3. Punching this, or you can distribute that. Okay, let me distribute. This will be positive, the negative like that will be positive. Then I distribute this, there will be 0,1 2 over 200 times 10 to the power of 9 P, right? But also if I distribute that negative will have positive. If it is positive, I multiply the whole inside, will be plus 0,1 2 over 200 times 10 to the power of 9 multiplied obvious by 4,539 P. All right, so now, because here if you will multiply this, there is P, and then you are adding, you can multiply this, like that. You can multiply that, or we're supposed to add, or okay, let us take this step further little bit. It's up to you which method you will take there. So if I punch this alone on the calculator, 112 200 times 10 to the power of 9, we'll have 6 times 10 power of minus 13 like this, right? Here we'll have P, then punching this there, zero comma 1 12, right? 1 2 and 2, that multiply this by what? By 4.539. We'll have 2,7,234 times 10 power of minus 12. Here we have P. Now we add these are like terms. This is a method of algebra. If we add this, what do we have? If we add that, we add now 6 times 10. Oh, right. or you can just, let's make this to be easy without wasting time. Just make p to be equals, you divide by this coefficient, we'll have 0, 1 times 10 power of minus 3, divide this whole by 6 times 10 to the power of minus 13 plus 2.734 times 10 power of minus minus 12. So if we do this same time, straight away we'll get the value. P will simply equals to 8,089 megapascal. We have that P now. So we know that force, we wanted to calculate the pressure, or the force in short, we wanted to calculate the force is equal to this. Now we have our pressure. How could then this will be coefficient of friction we have given to be 0.4. The pressure we have just calculated it now, times 10 power of 6 multiplied by pi, the common diameter there, which is now is in stretched was 0.12 times the length, which was 0.2 that we given. Then if you punch this, simply get this to be 907,458 kilonewtons. High order question a little bit. This is a high order, but not a high order question. As long as you understand your thing, you see we have been given the length here. It's not that much high coefficient, not that much high, guys. So for as long as you understand your things. So here question 2 says the torque that can be transmitted between the shaft and the sleeve. The torque, it's a one equation, but now you simply have to, it's a simply one an equation. Now you will have to divide. You know that the torque is equals to force multiplied by RC, common diameter, by RC is equals to what? To diameter, the common divided by 2. So the force we've just calculated is 9,7, not 907,458 kilonewton. Sorry, times 10. Okay, we will be in kilonewton. Let me just substitute as it is. Multiply common diameter is 0,12 divided by 2 is 0,016, or not 16, like this, 0,06. Then the torque will be 54,448. I've used this in kilonewton, so my answer I expect it to be in kilonewton per, since it's torque per meter. So this is what you have. So this is how it goes, guys. This is how it goes. If you're given, this is how it goes. So thank you for watching, please, and if you wanted to be a part of the family, please subscribe to my YouTube channel and click that notification button so that you'll be notified whenever I post a new video. I'll be happy if you subscribe, and feel free to comment and share this to your fellow classmates. Be a part of the family. Let's grow together. Then I will be keep on bringing this content for you guys if you support me. All the best. Thank you guys for watching.